them shits in pink. Yeah, got go ahead and go get a mink. Yeah, new finger rings it like a sink. Yeah, you a bad bitch, then we can link.
Hi guys, I'm back with another video, and today we're going to be talking about momentum and impulse. So let's define momentum and impulse. Momentum is defined as P equals mv, and impulse is defined as F dot t, which is really just F change in t, but I'm going to leave it in this form, which is also equal to mvf minus mvi, which is just the change in momentum. And that's the definition of impulse. So let's look at the boxing example again. If we have boxer A here, and he's punching a bag, and the punch is applied over time of, let's say, 3 seconds. He's a really slow puncher, right? The force that this bag will have to apply back is going to be a relatively small amount of force. Because if he's punching over, a distributed amount of time, over a long period of time, the bag doesn't have to apply as much force back and a much bigger force back in order to absorb the punches. So we'll call this force 1, and force 1 is over 3 seconds. Now we have boxer B here. And boxer B is a lot more experienced, he's a lot faster. He punches over 0.5 seconds. Now, in order to absorb this punch, the bag is going to have to output a much greater force. We'll call this force 2. And this makes sense if we look at impulse. Impulse, as we mentioned, is our force times our change in time. This means that if we're punching over a shorter period of time and our impulse remains the same, so we'll keep the impulse constant, if our time is greater, our force is going to be smaller, and vice versa. If our force is greater, our time is going to be smaller. And that's demonstrated in these two examples. So let's talk about momentum on the side here. Momentum is just the ability of an object, or the tendency of an object, to move. It's how hard it is to stop something. So if you have two walls here, and pretend these are the same walls, and you have two objects, each going at the same speed, at a velocity v, but one object is, for example, a car, and the car is going at 30 meters per second. Let's say that's our velocity, v equals 30 meters per second, and as a mass big M. And we have something smaller. We have, let's say, like a marble here. We have our marble, which is small m, going at 30 meters per second. Which of these has a greater momentum? Well, intuitively, you would say the car has a greater momentum, and that's because it's harder to stop a car. This wall will have to work harder in order to stop this car than it will to stop the marble. And if the wall isn't strong enough, the car will break it. The marble probably won't. So, in this case, our momentum of the car is big M times 30, and our momentum of the marble is little m times 30, and 30 times big M is greater than 30 times little m. So let's move into some problems and see how it applies there. Alright, so in problem 1, we're looking at a 0.5 kilogram object that experiences a 10 Newton force over 0.20 seconds. It's asking to find the impulse. Well, we define the impulse as F times our change in time. And in the scenario, our F is just 10, and our change in time is 0.20. So our impulse would be 2, and our units for impulse are Newton seconds or kilogram meters per second. That's also another unit for impulse. Alright, let's move on to our next problem. In this problem, we are given the impulse as 6.0 Newton seconds, and we're given the mass, and we're asked to find the velocity. So, we defined impulse as force times time, but we also defined it as change in momentum, which is mvs minus mvi. Now, the initial velocity is at rest, meaning that vi is 0, which would cancel out this entire portion. So what we're left with is mass times our final velocity is equal to our change in impulse, which is 6. If we solve this system, or if we solve this equation, we should get v equals 3 meters per second. And that is our answer. Okay, so we have a bit more complicated of a problem here. We have a baseball. A little baseball here. And it weighs, or it's massed at 0.15 kilograms. It's going at 30 meters per second. And we have a glove here. It's not going to be the best glove. It's just a low representation of it. Catches the baseball and stops it completely, right? And the time over which that occurs is 0.050 seconds. So what's the change in momentum of the ball? Well, change in momentum is just impulse, which is force times time, or the more appropriate equation here would be mvf minus mvi. And that's just because we have all the variables for that already. Our mvi would be our initial velocity, which we have. We have our mass, which is 0.15. Our VF would be 0 because remember this glove is completely stopping the ball. So by the time the ball reaches here, it has a 0 velocity. So we can cancel out this part of the equation. And when we solve, we get negative 0.15 times 30, which gives us negative 4.5 kilograms times meters per second, which is just the same thing as negative 4.5 Newton seconds, which is our answer. Now, quick note here. The reason our impulse is negative is because we are starting at a positive velocity and ending at, a velocity that is less than that positive velocity. So, if our velocity is going this way to the right, and our glove applies a force to the left to stop that ball, our impulse applied by the glove or applied on the ball would be negative because it contradicts the direction that the ball is already going. And that's an important concept that will come up. Okay, let's go to part B. So it's asking the average force applied. Now, we know that our change in momentum is our average force times our change in t. Now, where this change in t actually comes from is from calculus, and you can find the exact force at certain points using calculus, but for now, we won't be doing that. We'll just be looking at the average force. So just keep in mind, if you're solving algebraically, this force is the average force, not the force at a certain point. But that is what we're asked for, so we can just solve, using that. If we solve this equation, we get F equals our change in P over our change in T. We have our change in P already, or change in rho, I should say, since that's what impulse is defined as. Our change in rho is negative 4.5 newtons times seconds, and our change in T is negative 0.050 seconds. Now we can cancel out the seconds, and when we solve this, we get negative 90 newtons So that's our average force applied over the 0.05 seconds it takes for the glove to stop the ball. Alright, so let's go over a couple key takeaways to end off this video. Firstly, I want you to visualize the two scenarios that we talked about at the beginning of the video. We have a car going into a wall and a marble going into a wall. And I want you to think of the impulse applied by this wall at both points. So we have change in P equals F times T. And we have change in P equals F times T here. Let's say that the force is applied over, I don't know, let's just say it's applied over 0.5 seconds in each of these scenarios. So the car takes 0.5 seconds to crash through the wall, and same with the marble to bounce off the wall. In each of these cases, if the wall doesn't break, right? So let's say the car actually bounces off the wall here. The wall doesn't break. Which of these has a greater impulse? Well, obviously the car does. And that's because it's applying a force over a greater, or over the same period of time, but the force is greater than the force of the marble. If we have MVF here, minus MVI, it's explained the same way. Our car here has greater mass, and if it has the same final velocity, let's say both of these objects end at 0 velocity, the impulse on the car would be, would be a lot greater, and that's because this mass is greater. With the marble, the mass is smaller, meaning that the change in momentum would be smaller. Now, let's just look at one of these scenarios and apply it over different intervals. So let's say we have the marble crashing into the wall. And this marble has a constant impulse, right? Meaning that its change in momentum is constant. Its initial velocity, let's say, is going to be 30 meters per second. It's a fast marble. And its final velocity is going to be 0 meters per second. Let's say in scenario 1, the marble is stopped over time of 5 seconds. And in scenario 2, the marble is stopped over a time of 30 seconds. Even though both of these scenarios have the same impulse, and that's because they have the same change in momentum, the mass doesn't change, right? And the velocity changes the same way. One of these marbles is going to apply a greater force than the other one. And I want you to take a moment and think of which one would apply the greater force. So let's go ahead and solve this. If we have marble 1 has an impulse, which is defined as F times time. Marble 2 has the same. If the time is smaller and the impulse is the same, the force would be greater. And the time is smaller in marble 1, meaning that marble 1 hits the wall with a greater force. Or rather, the wall hits the marble back with a greater force than in scenario 2. So that's pretty much it for this video on impulse and momentum. If you do have any questions for me, leave them in the comments below, and I'll try and get back to you. I hope you enjoyed, and have a good rest of your break.
White diamond in them shits in pink. Got go ahead and go get a mink.